So these are the features of your Cortex M3 and M4 processor. Actually, basically, these two processors are designed by ARM. ARM is the Advanced RISC Machine. Okay, that is one of the manufacturer. Okay, so designed by ARM, which is built on a high performance processor core. Okay, so the processor core is the 32-bit RISC processor with 3-stage pipelining. So your ARM code follows 3-stage pipeline design. So what are the stages involved? 3-stage pipeline means what are the stages?
Fetch, decode, and execute.
Yes, fetch, decode, and execute. Okay, and so it follows a 3-stage pipeline architecture for fetching the instruction from your memory. And second one is about architecture. So it follows hardware bus architecture. So what is the significance of hardware bus architecture?
Pipeline feature.
Yes.
Pipeline.
Yeah, pipeline strategy can be implemented using this architecture. So that is this one allows simultaneous instruction fetches and data access, which means it has separate address and data bus. And some ARM code follows von Neumann also. The particular architecture ARM core processor follows von Neumann architecture. Okay, and third one is about instruction set. Okay, it follows thumb 2 technology. So the instruction set architecture in the Cortex M processor is called thumb 2 technology. That is thumb ISA. It is called thumb ISA. Instruction set architecture. So thumb 2 technology means it is like a mixture of 16-bit and 32-bit instruction. Okay. So it's a combination of 16 and 32-bit instruction. So that is called thumb 2 technology. So it supports thumb 2 technology instruction set architecture. So in earlier versions like ARM 7 and 9, has different instruction set. Just you look at this diagram. So this is the diagram. See, so this is the classic ARM processor. This is Cortex M processors. Okay, so we have two different instruction set. Okay, one is the ARM instruction set, another one is the thumb instruction set. Okay, basically this processor operates two mode. That is, it is in two state. That is ARM state and thumb state. Okay, ARM state means the processor will execute 32-bit instruction. Thumb state means it execute only 16-bit instruction. So the switching is required very often to change from ARM state to thumb state to ARM state. So the latency will be increased in case of conventional ARM processor. The performance is very low compared to Cortex M processor. Okay, so we have two states in the ARM 7 processor, ARM 7 or ARM 9. So these two processors are called as classical ARM processor. Okay, so during the ARM state, your ARM processor will execute only 32-bit instruction. Okay, so in thumb state, it will execute only 16-bit instruction. So there is a switching between ARM state and thumb state. So switching is required. That case, the performance will be affected. Okay. So, but in case of Cortex M4, it is possible to handle all the processing requirement without switching between two different operation states. Okay. So the thumb 2 technology means it's a combination of both 16 and 32 instruction. No state switching required. Is that clear, students?
Yes, ma'am.
Yes, ma'am.
So instruction architecture in the ARM Cortex M processor is called thumb 2. That is based on thumb 2 technology, which supports mixture of 16 and 32 bit instruction. Okay. And next, coming into the memory. So the addressing is, since it is a 32-bit processor, the size of address bus is 32. Okay. So it is capable of addressing 2 power 32. That is equal to 4 GB. So the memory space size is 4 GB. So what is the memory size of 8051 microcontroller? What is the flash memory size?
Okay.
4 KB. But in ARM Cortex M4, we have 4 GB of memory space. Okay. So this memory space is utilized by program code, okay, similar to your previous processes, data code, peripherals, and some of the debug support components. Okay. So the address bus sizes, since it is a 32-bit processor, the address bus size is 32. So it is capable of addressing 32 memory location. So 2 power of 32 is equal to 4 GB. Okay. And fifth feature is about bus interfaces. Okay. So it has on-chip bus interface based on ARM advanced microcontroller bus architecture technology. So which allow pipeline bus operation for higher throughput. Okay. So it has on-chip bus interfaces. Okay. And one more important component is the interrupt controller. It is integrated on the chip itself. So that controller is called NVIC, Nested Vector Interrupt Controller. Okay. So this device, actually it's an internal device. It supports up to 240 interrupt requests. Please note it down. These informations are very important to understand your ARM Cortex M4 internal architecture. Okay. So this supports how many interrupts? Totaling 240 interrupt requests. Okay. And this one is it supports optional memory protection unit to provide memory protection features. Using this unit, we can protect the memory. Okay. Memory protect the memory, that is your internal memory, RAM, SRAM, and flash memory. Okay, so to provide memory protection features like programmable memory and access permission control. Okay, and also it supports bit banding, memory bit banding. So support for bit data access into specific memory region using a feature called bit band. Okay, I will explain this later. So what are the features? So it follows 3-stage pipeline design, and the architecture is based on Harvard bus architecture, and the instruction set architecture is called Thumb 2 technology. It's a combination of your 16-bit and 32-bit instruction, and it is capable of addressing 2 power of 32 memory location, which is equal to 4 GB memory space. So this memory space includes your program memory, data memory, and peripheral memory, along with some debug components. And also it has on-chip bus interfaces based on advanced microcontroller bus architecture. And also it has a inbuilt interrupt controller. Earlier in 8051, we need to connect external microcontroller, that is interrupt controller, to access the interrupt request more than one. Okay, that case we need to connect external interrupt controllers. Here it has internal interrupt controller which supports 240 interrupt request. Okay, and also it has optionally have memory protection unit to access the permission control of all the memories involved in the Cortex M4, and also it provides bit banding logic, that is to access the memory, that is two specific memory regions. Using this bit band logic, we can access the bitwise data. Okay, so these are the features of Cortex M3 and M4 processor. Okay. So this is the internal block diagram of your Cortex M3 and M4 processor. Okay. So this processor, that is M3 and M4, contain the core of the processor. So this block is called core. So core of the processor, NVIC, nested vector interrupt control, and system tick timer. This will provides the clock cycles, and optionally we have a floating point unit. Okay. Okay. Apart from these, the processor also contain some internal bus systems. There is internal bus interconnect and optional memory protection unit and set of components to support software debug operation. This block is for debugging. Okay, this complete block is for debugging. So what is the purpose of this internal bus interconnect? Any idea? What is the need of this interconnect? See, the Cortex M3 and M4 processor don't include memory internally, okay? So they don't have program memory, SRAM and cache memory. Instead, they come up with a generic on-chip bus interface. So this using this bus interface, we can connect the external memory, okay? So microcontroller vendors can add their own memory system to their design, okay? So typically microcontroller vendor will need to add program memory. That is program memory is typically a flash memory, data memory typically SRAM and peripherals. Okay. So the bus interfaces on the Cortex M processor are 32-bit. Okay, based on this advanced microcontroller bus architecture that is called AMBA. Okay, AMBA. It follows advanced microcontroller bus architecture. Okay. So this AMBA contains a collection of several bus protocol specification. So we have 4 accessing here. Just look at this diagram: I code, decode, system, private peripheral, and debug access port. Okay. So this I code and decode is primarily for program memory. So using this interface, microcontroller vendor can add their memory externally. Okay. So this is for your flash memory. Okay. And this system interface is for RAM and peripherals. And this private PPB is for interconnecting peripherals. Okay. And here another interface, debug access port, is for connecting your debug components. Is that clear, students? So generally they don't have program memory, SRAM and cache memory. So microcontroller vendor, based on their requirement, they need to connect the flash memory and RAM peripherals, okay, using these 5 interfaces, internal bus interconnect. So the using this internal bus interconnect, we can connect program memory, SRAM and peripherals, okay, and private peripheral devices and debug components, okay. So the important component involved in this architecture is NVIC, okay. So it is used to deliver industry-leading interrupts, okay. So all the interrupts are non-maskable interrupt, NMIs. All the interrupts are non-maskable interrupts, so it can provide up to 256 interrupt priority level. Okay, so here I have mentioned 240. Okay, so remaining 60 is for high level interrupt priority. To 40 plus 60. So it can provide up to 256 interrupt priority level. So the tight integration of processor core and NVIC provides a fast execution, the faster execution of interrupt service routing, which will reduce the interrupt latency. Okay.
Ma'am,
Yes.
And what's a non-maskable interrupt, ma'am?
Actually, a non-maskable interrupt means it cannot be disabled by user or programmer or the processor side. Suppose during the execution of non-maskable interrupt, microcontroller vendor or user or programmer cannot disable the interrupt service routine execution. Okay. Suppose maskable interrupt means actually we have two instructions, enable interrupt and disable interrupt. Okay. During the execution of non-maskable interrupt, this DI instruction is deactivated. We cannot disable the interrupt source. So that is the meaning. Non-maskable means we cannot disable the interrupt source. Is that clear?
Yes, ma'am. So which is better to employ, ma'am?
Actually,
Maskable or
for critical code execution, we need to assign a particular interrupt source as a non-maskable. Suppose if the processor is doing any emergency work, suppose let's take the airbag example, okay? So processor is doing some emergency work. So that case, the particular interrupt cannot be disabled. So during the program, the DA instruction is deactivated. So when airbag should be activated within a few minutes. Suppose that particular interrupt is disabled that time, okay? So the entire system will be collapsed, okay? So that interrupts are called non-maskable interrupt. So during the emergency, during the execution of critical code, some of the interrupts will not be, that is, cannot be disabled by the programmer, okay? Is that
yes,
clear? Just consider that airbag example, okay? So that is the best example for non-maskable interrupt, okay? Is that clear, students?
yes, ma'am.
Okay.
Yes, ma'am.
So this memory protection unit, okay? So look at here. So this is the memory protection unit. So it is an optional feature available on the Cortex M3 and M4 processor. So microcontroller vendors can design whether to include this memory protection unit or not. Suppose if the unit is included, your application can divide the memory space into number of regions, okay? And also define the access permission for each of them. So based on the access permission, we can access the memory, that is data element stored in your memory, okay? Is that clear? So it's mainly for, that is mainly it is used to prevent the accidental erasure of data in SRAM or overwriting of instruction codes. So that's all about your memory protection unit, okay? So these are the various bus interfaces involved in your Cortex M3 and M4 processor. I code is for program memory. Okay, so the address ranges from 0000 to 1 along with 4 heads. Okay, so based on advanced microcontroller bus architecture 3.0. Okay, and D code is also for program memory, same address range, and it is based on AMBA 3.0. And system interfaces mainly for RAM and peripherals. Okay, so address ranges from 2 along with 7 zeros and 8 heads. Okay, so based on AMBA bus. And next, private peripheral bus interface for external private peripherals. Okay, so the address ranges from this to this. And next one is the debug access port for accessing debugging components, that is system memory and debug components, based on core site debug architecture. So these are the various bus interfaces available on Cortex M3 and M4 processors. Is that clear, students?
Yes, ma'am.
Okay. So my question is, how do you differentiate the terms processor core, okay, and processor? How these two terms are different from each other? Processor core and processor. So According to this diagram, which one is processor and which one is core?
Processor core is the highlighted region, ma'am, which
Yeah.
corrects.
So what are the components inside the core? So what
Uh,
is the purpose of this component?
we have different hardware architecture pipelining over there and memory interface.
Okay. What is processor?
The entire thing is the
The
processor.
entire thing is called CPU or processor. Okay. See, this block diagram clearly indicates that the processor is nothing but your processor core, which is surrounded by lot of peripherals. Okay. So this is your core. This is your Cortex M3 M core. So the processor is the combination. There is nothing but your processor core, which is surrounded by lot of peripherals. What are the peripherals? Your NBIC, okay, breakpoint unit, system tick timer, okay, internal bus interconnect, memory protection unit, okay. So the definition for this one is your processor represents core plus peripheral. So this highlighted portion is called ARM core, okay. So your ARM Cortex M4 core is surrounded by various peripherals. Okay, so it's surrounded by lot of processor specific peripherals. Okay, so my question is, what exactly there inside your Cortex M4 core? Please tell me what are the components inside your ARM core?
Pipeline, ma'am.
Okay. So this part is called your ARM Cortex core. Okay. So your Cortex M4 core is actually the basic computational engine of the processor. Okay. So it consists of its own register sets first. So register sets, it has many registers and ALU, okay, where the computation take place, and barrel shifter. So it is a hardware device. It will perform shift operation in order to improve the multiplication and division. That is speed up the multiplication and division operation. Pipeline engine, okay, and various registers to manipulate data, okay, and special function registers to track the execution state of the code, and also instruction decoder to decode the instruction. So all these components are actually part of the core. Okay. So this one is the single core processor or multi-core processor according to this diagram.
Single core processor.
It is a single core. So there is only one core. It is called single core processor. So the CPU may have multiple cores also. Okay. So in this case, this Cortex M4 consists of only one core. So this CPU is called single core CPU. Okay. So can you understand the difference between the terminology core and processor? So this entire thing is called processor, okay, and this is called core. So this core may be a single core or multiple core based on the requirement. The microcontroller vendor can integrate either single core processor or multi-core processor. Okay, is that clear?
Yes, ma'am.
Okay, so next one, processor versus microcontroller. So ARM is a microcontroller or processor?
Processor.
Processor. But sometimes, let's take the example STM microcontroller, LPC microcontroller. Why they are saying that the word microcontroller? But the chip IC involved in that particular board is the ARM. Why they are calling that particular component as a microcontroller? How do you differentiate that?
In microcontroller, we have all the components embedded in it, whereas in
Okay.
processor, we have to externally add
So
the.
already this is the complete processor is available. Why don't we call it as processor? This entire thing is available along with core and all peripherals. So let me explain this. Okay. See, the processor actually, this part, the core is designed by your ARM. This particular core is designed by ARM. The core, all its associated peripherals, actually in the software IP format. So IP format means intellectual property format. Okay. So the entire that is your core along with peripherals. Okay, actually in the software IP format, okay, which will be passed on to the various microcontroller vendors. Okay, various microcontroller manufacturer like ST Microelectronics, Texas, NXP microcontroller, like that. So this design, IP design format will be passed on to the various microcontroller design. So this software IP format of this particular design will be purchased by those microcontroller manufacturer. Okay, so they will integrate this engine into their microcontroller. Okay, so during the integration, the complete design is called microcontroller design. So they may remove some of the components, or they may include some of the components. So while integrating this engine, that means this CPU design with their microcontroller. Okay, just look at this STM microcontroller IC. So this is STM processor, that is STM32F446RE. So we are going to use this particular hardware in our lab. So this board is called Nucleo board. Okay. So it is a ARM Cortex M4 core with DSP and floating point unit and 512 kilobytes of flash memory, and the frequency is 180 megahertz CPU and accelerator, inbuilt accelerator, and dual QSPI. So this is first some signal processing application. Okay. So just you download this data sheet and go to the functional block diagram. So this is the functional block diagram of STM32F446RE. Okay. So look at this block diagram. So the heart of the microcontroller is your CPU. Okay. So this block. CPU, which is nothing but ARM Cortex M4. Okay, so this unit is actually taken from taken from ARM. Okay, so this part. So this is taken from ARM. Okay, and the rest all are implemented by ST Microelectronics. All the peripheral devices are connected to this particular processor. Okay, so this engine actually, that is a CPU engine, interfaces to ST implementation by using three bus interfaces. Just look at here: I bus, D bus, and S bus. Okay. So this is the software IP format given by the ARM intellectual property software format. So, and these implementations are actually done by ST. So, and they both meet at these bus interfaces. All the devices are communicating with ARM Cortex M4 through this bus interface. Okay. So here ARM Cortex M4 acts like a master, and all other peripherals are actually slave to the master, that means to the CPU. Okay, so they both communicate through various bus interfaces. So here you can see it supports many ports: port A, port B, port C, D up to H. And also we have timer devices, serial communication devices, and inbuilt ADC, and timers, okay, crystal oscillator, and so based on their requirement, they can integrate all the units to this particular ARM Cortex processor. So this is taken from ARM, reminding all the implementations are actually done by STM microelectronics. So this complete block is called microcontroller. So hope you understood the difference between processor core, processor and microcontroller. Is that clear, students?
Yes, ma'am.
No.
Yes, ma'am.
So these are the components available in your Cortex M. So externally, we can connect these memories using bus interfaces. There is flash memory, non-volatile memory, instruction memory, data memory, okay, along with your processor. So these are all under your core. So the core contains ALU, processing control unit, and all your special function register and general purpose registers. Okay, and your ARM supports advanced high performance bus and advanced peripheral bus. Okay, and we can connect these peripherals to Cortex M3 and M4 processor through using these bus interfaces. So just you look at this diagram. See here, this is the ARM core designed by ARM. Okay, and remaining components are designed by chip manufacturer. That is your memory. So everything is integrated on a single IC. So this IC is called system on chip. So it contains ARM core. It can be ARM 7, 9 or Cortex along with system peripherals and analog devices and serial interfaces with external memory. Okay. So everything is put into a separate box. Okay. So this IC is called system on chip. So this can be called as ARM microcontroller. That is ARM based microcontroller. And this core is called processor. See, coming into the memory, okay. So this is the memory structure. It's to be followed in your Cortex M3 and M4. So the memory address size is 32-bit and each memory location can hold 8-bit data. Okay. So it is a byte addressable regime. So in this example, that is 800AD, we have data 01, okay. 1B0, we have 70. So hexadecimal representation, that is 112 in decimal, okay. So the memory size is 4 GB, okay. So it's capable of addressing 2 power 30 memory locations. That is this much amount of memory locations. So the entire region is divided into program memory, data memory, peripheral memory, and debugging memory, okay. So you note down the questions. Tomorrow we will discuss the answer. So this is the memory mapping of your ARM Cortex M3, M4. It's 4 GB memory. Okay, it is divided into flash memory, EEPROM, SRAM, and some of the memory regions for that is allocated for special function register. Just note down all the questions. Okay, we will discuss the answer in the next class.